Okay, now you all know that we're going to run out of time, and I'm not going to get to, somebody called it my mic drop moments at the end.
Yeah.
They said you need to hurry up and get to those before people have to leave. So, so we're going to talk about. So we're going to talk about stuff related to Hawking, who many of you know passed away on the 14th. The first thing you should understand, if you don't already know this, but you're mostly physics people, so you know this, he was a real physicist. Like, he did some very, very, very important, very, very hard stuff. Of course, he also wrote popular books. And, you know, within the scientific community, there's always a bit of a debate, like, you know, should you be dumbing down physics to make it appeal to a broader audience? And I feel like, personally, it's important that he wrote those books, because reading one of those in 11th grade is what actually got me interested in physics. And so it certainly acts as a segue to draw people into the field who otherwise might not end up in physics. Of course, I remember reading that book in 11th grade thinking, oh, I can do this. I don't need math. I just think of interesting shit and weird pictures, and you know, and I can do this. And then I went to Georgia Tech and started studying physics, and we talked so much about balls rolling down inclined planes. I was like, where's the black holes, man? But, you know, after 11 years of studying physics and math, you know, I eventually got to the interesting stuff. And truthfully, I ended up studying things which were way more interesting and bizarre than anything I saw in his book. But at any rate, I think it's important for people to do these popularization tasks. I always feel like they have to have some scientific credibility under their belt, you know, in order to take their popular exposition seriously. If you really don't know what you're talking about in the first place, I don't believe your efforts to dumb it down. And then, of course, you should all take a moment to reflect on the fact that this guy did a lot of what he did. In fact, the most important result we'll talk about today was done like while he was in the more severe degenerative stages of his disease. So if you think physics is hard, think about doing the hardest parts of physics at a point in your life where you can't even really write. So someone compared it to Mozart's alleged ability to compose entire symphonies in his head. You know, that's essentially the task Hawking had. Like, he couldn't write down, make a mistake, erase it, go back. Most of this was being cranked out in his head. And he did have the ability to communicate, but it was really slow. Okay, and I saw this firsthand in a lecture that he gave at Caltech. And I personally have no doubt that if he hadn't gotten ALS, he probably would have, you know, been one. He was arguably one of the greatest physicists of the 20th century, but he would have done a lot more than what he even accomplished. And I am furthermore convinced that at some point he would have taken up the mantle of either loop quantum gravity or string theory. He wasn't really in either of those camps. He didn't do a whole lot with quantum gravity per se, and I'll talk about what that is in a few minutes. He kind of had the tools that he had developed by the time he got sick, and then he worked as much with those tools as he could. He did, of course, you know, learn a few other things, but it's striking how many important results he got without ever really kind of jumping into either of these fields of quantum gravity. But no doubt, had he not gotten sick, I'm sure he would have progressed into one of those fields. Okay, so what did Hawking work with? And it turns out that his work was largely combining two particular frameworks for doing physics at the fundamental level. First of all, he worked with the context, or he utilized the context of non-gravitational quantum field theory. And I'll talk a little bit more about what I mean by that in a moment, but essentially this is a way of doing quantum mechanics at sort of the fundamental level where you treat everything as fields instead of particles. But the framework itself does not allow for the effects of gravity to arise, okay? And then secondly, he was, of course, an expert in classical general relativity, which was Einstein's theory of gravitation, and you're all kind of cursorily aware of the words, matter and energy curve space-time, and then the curvature of space-time is what gives rise to the influence of gravitational or gravitating bodies on test objects, because they move differently when they're moving through a space-time which is curved. So Now what's important is, when Hawking was doing his work, everyone agreed on QFT. Like, no one said QFT is crap. Like, everybody agreed that the predictions that had been made and tested by quantum field theory, particularly in the context of quantum electrodynamics, they were spot on. Like, this was the correct way to at least describe everything except gravity. And everybody agreed that if you're only focusing on gravity, this is definitely the correct description. And it had been experimentally verified to high precision. So he was working with two tools about which there was little fuss. Now that's in direct contrast to, for example, quantum gravity, where you're taking gravitation itself and treating it quantum mechanically. And I'll just typically refer to that as QG. And folks who do calculations in quantum gravity, they get far less street cred because there's no yet firmly accepted framework for quantum gravity. There's a couple of contenders, loop quantum gravity. Well, there's a contender string theory and another loop quantum gravity. But anyway, even string theory is not widely accepted. So if you work in quantum gravity and you make predictions, there's not a lot of people, or if you point out problems, there's not a lot of people that are going to take you that seriously. But what Hawking was working with was two theories that were perfectly well accepted at the time. And what's important is that by working with those theories, he actually discovered some really fundamental significant problems. And those problems were taken seriously by the rest of the community. Okay, so I'm going to try and be like chop so I can get through all this. So if I'm speaking quickly, there's a good reason. And I have to get to the end because the end is where the money is. Okay, so very quickly, here's my 45-second introduction to general relativity. For some folks in the room, this is going to be a refresher. For some folks in the room, this is going to be horrifying. But here it is. This is general relativity in a nutshell. If you've ever seen any of the Nutshell series textbooks, it's laughable because general relativity in a nutshell is almost 700-800 pages long. It's ridiculous. So this is general relativity in a nutshell. And this is no doubt using some convention for units that I might or might not have adopted in my general relativity class. But this is Einstein's equation. This R mu nu and this R, this is the Ricci tensor, the Ricci scalar. These are just built out of derivatives of this thing G. Lambda is just a constant. And T mu nu is the energy momentum tensor, which encodes the presence of mass and energy and momentum, all the things that can actually give rise to curvature. And the way that we work with this equation is normally we say, given a T mu nu, that is, given a collection of matter and energy and momentum, like given planets and stars and the cosmic microwave background radiation and all this stuff, plus some boundary conditions, we solve this equation for the unknown G mu nu, and that G mu nu is the metric tensor which describes the geometry of the space-time. Okay, so we specify the sources, we solve this rather straightforward and simple differential equation to find this tensor solution, and that tensor is actually a description of the resulting geometry. And there's in the second part of this where you can now ask, how does this geometry describe the motion of test particles on that? And then we solve the geodesic equation, but we don't really have to add that part of the story for today. Okay, so any questions about GR? Good. So quantum field theory, and just to write down an example, if we consider the quantum theory of electrodynamics, then we first can write down the Lagrangian governing this theory. Oops. New beta. Okay, so we have a Lagrangian which sort of defines our theory, and then from that Lagrangian you can vary it, you take the variation, set it to 0, and get the classical equations of motion. But if you were to do a quantum version of this, what you typically do is you could cram this into a path integral. And so when we work with quantum field theory, more often than not, we're considering the answers to questions like, for example, if I have two electrons, which I kind of shoot towards each other, then I want to perhaps calculate the probability that afterwards I have two electrons coming out. This is relativistic, so the particles that are present can change. You don't have to end up with electrons, so this is just one of many possibilities. And in the quantum field theory context, we calculate the probability of that particular outcome. And I should say these are sort of the boundary conditions. I'm sending two electrons in with certain energy and momentum. And we calculate this by looking at all possible ways of filling in this diagram. And so for reasons which my class in particle physics will become more familiar in the days to come, there are a host of contributions. The electrons can just interact by the exchange of a photon. That's the electromagnetic interaction of leading order. But then you can have some more weird things happen. That's certainly not the only possibility. The photon being exchanged can be interrupted by the creation and annihilation of an electron-positron pair. So this gives another contribution. And in fact, any of these external lines that I'm drawing, I could interrupt with a virtual photon emission and reabsorption. So there's a bewildering array of these things, and then there's a logical organization where you make the more complicated diagrams to the right by order of increasing number of vertices. And then for each and every one of these, you calculate a quantity. So each of these really represents a number at the end of the day. And then you add up all those numbers, and that is going to give us the quantity mi, which is the quantum amplitude for this process to occur. Okay? So this is the quantum amplitude for this process to occur. Now, what's very important about the quantum mechanical story is that we're never allowed to ask what happened. All of these contribute, even though you would say, oh, but this happening is very different from this happening. The only thing we know is that two electrons came in, two electrons came out. That's the physical reality. And the probability of that physical reality has to take into account all of these possibilities. We are never allowed to ask which of these particular mechanisms was the one that did it. In fact, they all happen sort of simultaneously and contribute together. That's going to be a very important observation coming back at the very end of this talk. And then, of course, you can take this and you can cram it into Fermi's golden rule, and you can calculate the scattering cross-section associated with this, and then get some real numbers to compare with the experiment. But what I want to do now is kind of go back to, well, what was it exactly that Hawking was dealing with? What did he do? So Hawking was clearly working with both of these frameworks, quantum field theory, so looking at these kinds of calculations, but then the context of classical GR here. And what he did was he combined them. He put them together. Okay? Now again, not quantizing gravity, but rather using quantum field theory for all matter and interactions except gravity. So for example, he would quantize the electromagnetic interaction, the strong interaction, the weak interaction. He would treat electrons quantum mechanically, neutrinos quantum mechanically, et cetera, et cetera. And then he would do two things. He would first of all assume a non-dynamical curved geometry. Okay, so most of the calculations that you do in particle physics assume a flat geometry, a very boring Minkowski simple geometry. Okay? But of course, the important thing about general relativity is that you can get these really interesting curved geometries. However, of course, the important part of general relativity is it tells you where those curved geometries come from, and it allows you to describe the dynamical evolution of those curved geometries. He's working sort of in a hybrid. He's saying, okay, I'm going to take a curved geometry. I'm not going to ask where it came from. and I'm not going to allow it to evolve, but I'm just going to work on a curved geometry, okay? And then he introduced the effects of gravity, because if I have a curved geometry, I have gravity. And he introduced the effects of gravity in sort of the canonical way. And those who've taken general relativity know how this works. You take the normal metric of flat space-time, which appears here, and it's also sort of buried in here, and you replace it by the curved metric of the curved space. So this expression is written in flat space-time, and you just generalize it to what it would look like in curved space-time. And so that means replacing the metric with the curved metric. And then it also means that anytime you encounter an ordinary derivative, you need to replace that with a new derivative, which is corrected by the Christoffel connections, which are built out of the curved metric. So these are details that are not that important for today's discussion. But the point is that what he was doing here was perfectly well accepted. Like if you can do quantum field theory on a flat space, you should be able to do it on a curved space. Because again, we're not doing dynamical gravity. If you're trying to do quantum dynamical gravity, that's quantum gravity, okay? To introduce the effects of curvature, like what is curvature doing to the story, he just made this replacement, which was a canonically accepted way to fold in the effects of curvature. Nathan?
Yeah, so the Christoffel symbols just basically go in right next to the gauge field of the covariant derivative?
Yeah, so this covariant derivative becomes this really hideous thing. It's got the correction from the gauge field itself plus the correction from the Christoffel symbols. So I'm not even going to write it down. Okay, so one of the more pronounced effects that happen when you start looking at quantum field theory in this context on curved space-times is that the very notion of what the vacuum is gets sort of upended. So we can all agree, and in flat space for inertial observers, this is sort of universally accepted. Oh man, Will's not here, is he? Damn it, I was hoping to have all three of you here. We'll have to beat up Will later, but anyway. There's sort of a universally accepted idea of what the vacuum is. I mean, what's the vacuum?
Empty.
The vacuum is empty. There are no particles there. Of course, here what we mean by particles are fluctuations of the fields, localized fluctuations. But nonetheless, in ordinary quantum field theory, all inertial observers will agree, you know what, the vacuum is the state where there are no fluctuations, okay? However, in curved space, it's not that simple. To explain the effect in curved space is difficult, but you can actually see an analogous story play out in flat space. And so what we discover is in flat space, so in four-dimensional Minkowski space, this is the space of special relativity, it's flat, we can take an inertial observer, and we know he's inertial because he's standing at rest on the ground. I'm just kidding, that's in physics 1, like the inertial observer is always the person standing on the ground, despite the fact that the ground is part of the earth and the earth is moving and the earth is spinning anyway. Okay, so, and this person looks at the vacuum, the vacuum, and he sees the vacuum, right? I mean, this person looks at the vacuum, there's nothing there. Can't put a hand in my pocket, what did I find? Nothing, there was nothing there. Okay, now we take Susie Speedster, and she is not happy being an inertial observer. I'm almost drawing a swastika, that's kind of and she is not just hauling ass to the left, but she is going to be accelerating. After all, constant velocity is still inertial. You got to be accelerating. And here's what's crazy, and what's crazy is I can't even draw it. She looks at the same thing. These two people are looking at the same friggin' thing. But what they see is different. This guy sees nothing. He's just like, I don't see nothing. She sees radiation of particles moving at her. To her, the vacuum is a stream of particles moving towards her. Particles, fluctuations, things that exist. They're looking at the same thing. One sees nothing, one sees something. Okay? It's bizarre, but it falls directly out of an application of quantum field theory in the reference frame of an accelerated observer. Okay?
In curved space-time, or?
No, in flat space-time.
Okay.
However, in curved space-time, the equivalence principle, well, actually, I'll come back to it in just a second. But that exact statement is on the next page, so let me come back to that in a minute. Okay, so this effect, of course, is called the Unruh Effect, if you want to read about it. And this kind of radiation is called Unruh radiation. And by the way, this radiation is radiation of every kind of particle in the theory. So it's electrons, it's photons, it's neutrinos, it's everything comes out. Everything that's part of your quantum field theory is part of this radiation spectrum. Okay? And in fact, it's thermal radiation, which means that its temperature, or sorry, its spectrum, how much of each of these components of the radiation are present for different frequencies, its spectrum is completely determined by a single parameter, its temperature T, which is related to the magnitude of the person's acceleration. Okay? All right. So, you can do quantum field theory on curved spaces. We anticipate there's going to be some effed up things happening. But of course, what's the most interesting curved space that we should be applying all of this to? The black hole, the Schwarzschild solution. Okay? So that's what Hawking did. He took all of this and he said, all right, let's put it on a black hole and see what comes out. Okay? So for those of you who aren't familiar with black holes, and I know that there's a handful in the room, let me just give you the quick and dirty on a black hole. And it's encapsulated in two words: gravity sucks. Okay? And what I mean by that is gravity affects everything universally, and in particular it tends to clump things. The only exception to that is vacuum energy, which actually creates a repulsive force, but that's not really going to be a relevant part of the story. And so what's important is if I take a bunch of stuff, matter, energy, whatever, and I let it get close enough so that its gravitational interactions become important, it's going to act to collapse itself smaller and smaller, because the gravity of everything is pulling everything else closer and closer. Now, of course, that, for most objects, stops. You are not gravitationally collapsing. We are not gravitationally collapsing to the center of the Earth. And that's because there are other forces in the story which can act to repel this stuff. And so, of course, the most common way to stop collapse is through electromagnetic interactions. So the outward electromagnetic forces, in most contexts, are sufficient to stop things. But if you get enough stuff together, you can actually overcome electromagnetic forces. And then as things get smaller and smaller, eventually you get to the point where you're trying to take electrons and put them on top of each other in the same place, in the same state. And we know that the Pauli exclusion principle forbids that. And so you can also be stopped at a much smaller size by the Fermi degeneracy pressure. And if you're fortunate enough to get stopped there, then you're left as a white dwarf. But if you started out with too much mass, even this Fermi degeneracy pressure can't stop you. And so you get smaller and smaller until eventually you're trying to put neutrons on top of each other. And at that point, you can have neutron degeneracy pressure stop you. And if that happens, then you're left with a neutron star. But if you start out with enough mass that you can't be stopped by a neutron degeneracy pressure, you're going to eventually collapse to a point, and that's a black hole. Okay? Any questions about black holes? Okay, so we take this stuff, and it's collapsing down, and then eventually it's that. Okay, and I can't draw that small enough. It's a mathematical point. It's a singularity. It's got zero size, and yet it's got, mass many times the sun crammed in there. Okay? There's a lot of problems with this. Zero mass collections of things, or zero size collections of things, are really hard to treat with smooth theories like general relativity. The curvature of this space-time radically diverges as you get near this thing. Okay? So near this singularity, all of physics, but in particular GR, breaks down. So if you want to try and describe what's going on a gnat-sass away from the singularity, general relativity is not going to do it for you. And of course, this whole framework that Hawking was calculating in, quantum field theory on a fixed geometry, that's not going to work. Okay? In principle, to describe what's going on at or near that singularity, you actually have to have quantum gravity in your pocket. Okay? However, this is not the only important part about a black hole. It turns out that the most important feature of a black hole is that it is surrounded by an event horizon. And we all roughly know what an event horizon is. If you're outside of the event horizon, you can, if you want to, escape to infinity. But the moment you get inside of the event horizon, you can no longer get back to infinity. In fact, once you're inside the event horizon, there's only one direction you can move, even if you sit still. Sitting still is going to the center. In fact, moving outwards is going to the center. In fact, moving outwards is going to the center faster than sitting still, strangely enough. Okay? So once you're inside of a black hole, the shit hits the fan. Very weird stuff is happening. But what's crucial about the event horizon is that out here, in the neighborhood of the horizon, this does not have to be strongly curved. In fact, if I take a very supermassive black hole and you drift into its event horizon, you might not actually realize you've passed the horizon. So normally the way you know you're inside of a black hole, and you've probably all heard this story, is as you get near the singularity, your head is feeling a different gravitational force than your feet. And it's the gradient in the difference between the force on your head and the force on your feet, what we call the tidal effects, and that's just going to rip you apart well before you get to the singularity. Okay? So the idea is that for a supermassive black hole, you can cruise through the singularity, and these tidal forces are so small that you don't even really physically notice it. I mean, of course, stuff's going to get weird. Okay? Because like if you look towards the singularity, you can't see anything coming towards you. But you can look outside the black hole and see stuff coming in. But locally, the curvature's not being weird. The importance of that observation is that in this region, the kinds of calculations Hawking was doing should work. It's perfectly feasible. You have no business trying to do it near the singularity, but near the horizon, it should be good, at least for a supermassive black hole. Okay, and that's what Hawking did. Okay, yes. And then, okay, so Hawking did this. He said, I'm going to take GR and quantum field theory, and I'm going to apply those lessons near the horizon of a black hole. And the conclusion that Hawking arrived at, you can kind of get in two different ways. And neither of these are exactly what Hawking did in his original paper, but they're both suggestive of the same result. So the first thing that you can say is, well, if I've got a black hole with some event horizon, quantum field theory tells me that in the vacuum, I'm always free to create and annihilate particle-antiparticle pairs. So I might create an electron and an anti-electron temporarily. They've come out of the vacuum and then they disappear back into the vacuum. But of course, if this happens close enough to a black hole, then one of them, say the positron, could actually end up dipping inside of the horizon, after which it's gone. Okay? But what happens is that in this process, what was a virtual electron is now promoted to a real physical electron, because it is no longer sensitive to the fact of, hey, I need to find this guy and annihilate with him. And so this guy can happily wander off to infinity. Okay? Here, as long as they both remain outside of the black hole, they are going to find each other and annihilate. Okay? Alternatively, we can say the following. If I have a black hole, there's some gravitational field. Okay, this is not Newtonian gravity, it's very different, but nonetheless, there's some gravitational field at the horizon, but the equivalence principle tells me that I can freely interchange the effects of gravitational field with the effects of acceleration. And what we've already learned from the Unruh effect is that if you do quantum field theory in an accelerated frame, you see radiation. So either way, you come to the same conclusion. The black hole is actually radiating. It's giving out particles. And again, it's not just light. It's light, it's electrons, it's protons, it's everything. Okay? Of course, the spectrum is going to be dominated by the lightest mass things. All right? But nonetheless, Hawking's result, and this is, presented circa 1975, a year after the greatest event in the history of mankind. That's a joke. I'm not nearly that old. Anyway, so the result of both of these is that black holes are actually not black. Black holes ain't so black. Okay, they're actually radiating. Moreover, what Hawking demonstrated, and again, Hawking's calculation was much more rigorous than what I'm showing you here. And even Hawking proposed this cartoon picture in his original paper and said, by the way, be really careful. This is not completely accurate. So really, he's like, this is a cute cartoon. You should read the details in section 2. He literally says that in his paper. It's pretty funny. Anyway, so when Hawking did the calculation to predict this, the other thing that he observed is that the radiation is thermal. And again, what we mean by thermal radiation is that the spectrum of radiation is completely determined by a single parameter, T, the temperature. And then Hawking connected that temperature to the mass of the black hole. One number for one number. A black hole has a mass, therefore it has a temperature. If it's got a temperature, it's radiating. This is the whole story of black body radiation, which I'm leaving out because people who've never heard of it are like, is black body radiation, black hole radiation? What do you mean? It's a different thing, but it's the same thing in this context. Okay. All right, so black holes radiate. So what? Okay. Well, here's the problem with the black hole radiating. For large black holes, the black hole itself is radiating, but it's actually radiating very slowly. Black holes have this weird property. That large black holes are actually cooler than small black holes. The bigger you get, the lower your temperature. But the lower your temperature, the lower your rate of radiation. So large black holes are radiating much more slowly than small black holes. But conversely, large black holes are also accreting matter in. I mean, if nothing else, there's the cosmic microwave background radiation. There's a bath of photons throughout the universe. And so a black hole sitting there is drawing in these microwave background photons. So it's adding to its mass and energy. It's losing through radiation, but it's adding much more quickly than it's... So a big black hole is going to live forever. It's not going to go anywhere, okay? For tiny black holes, which can form, tiny black holes radiate so fast and they are bringing in stuff at such a low rate that they will actually disappear. They will evaporate, is the term. Okay? Now, you might say, well, can tiny black holes truly form? Oh, no, we definitely know big black holes exist. Okay, they've been detected. But for purposes of sort of foundational arguments, we could just ask the question, suppose I had a big black hole in truly empty space, where there was nothing for it to draw in. Then it would radiate and eventually disappear. And when we think about that, we reach a very serious problem, okay? So physics has got a lot of conservation laws. And what we know roughly about a conservation law is that the change in some quantity is always related to the flux through a bounding surface of the system. Okay, that's what we mean by a conservation law. If a quantity is changing, we can explain that change by saying something is leaking out of or coming into the system. Okay? So my favorite example is, of course, the number of people in this room is conserved. The only way it can change is for you to leave the room or people to come in the room. But of course, it's not actually conserved because you can procreate. But anyway, that's what we mean. Okay, so, all right. Now, conservation laws are very deep in physics, and we are very, very reluctant to give them up. And sometimes that causes us to do crazy things. So, of course, the most famous example of this is back in the day when a neutron was observed to decay into an electron and a proton. People looked at this process. This is a neutron at rest. People looked at this process and said, wait a minute, this doesn't satisfy conservation of linear momentum. There's a reason why I drew these two things at a weird angle. If this is a single thing decaying into two things, they should shoot out back to back. Okay? And there were some people who said, well, you know what, maybe linear momentum's not conserved. Okay, but Pauli said, no, damn it, it is. And I'll find a way. So what did he do? He invented an invisible particle to carry away the missing momentum. And that, of course, was the anti-electron neutrino, which was later observed. So when people make bold suggestions in order to preserve conservation laws, they're usually right, even if it sounds whack. Okay? So what has that got to do with this black hole story? Well, first of all, there's an immediate consequence for conservation laws. And that is, if I take the system, as everyone in Physics 1 is wont to do by a certain point in the course, to be everything, where by everything I really mean the entire universe, then what can you say about a conserved quantity?
It's really conserved. I don't know.
It's
Not changing.
constant. Yeah, because if you take your system to be the entire universe, there's nowhere for stuff to go or for stuff to come in from. So if your system is everything, conserved means constant. Okay? Now, one quantity which is actually conserved, although it's not one that you're perhaps as familiar with, is the idea of information. Now, what do I mean by information? Well, I could take a perfectly spherical uniform mass, M, all right, and this could be so perfect, you know, maybe it's made of a single atom in a perfectly regular structure, so there's really very little information to give you except for its size or its mass. You can interchange those two things. And then I could, of course, give you another structure
It's a cow.
which happens to have the same mass M, but is much richer in information. You know, this is a spherical cow. Its spots are in certain places. It's got 4 legs instead of 3. It's, you know, certain color patterns. You know, there's a lot of information here, even though these have the same M. Okay. So the idea of information is sort of how much extra detail do you need to specify in order to be able to distinguish this case from this case. That's information. And although it's not a quantity you normally work with in classical physics, in quantum mechanics, information becomes a very important quantity. And it turns out that information is conserved, and this is also reflected in the unitarity of quantum mechanics. That is, if we start with some wave function, its time evolution is governed by unitary transformations, which can be reversed. You can evolve the wave function forward in time or reverse it and evolve it backwards in time. And the amount of information in the wave function doesn't change. Now, that is interrupted if you make a measurement, because there's some wave function collapse that can't be undone. But we're talking about outside of the context of measurement. You just let the thing evolve. Do you lose or gain information? The answer in quantum mechanics is no. And it's directly tied to the idea of unitarity. Okay? Okay, so why is this a problem for a black hole? Well, if we have a black hole, we can imagine taking one of these two objects and throwing it into the black hole. Okay? Now, what's going to happen to the black hole is that the black hole is going to get a new mass, which is the old mass that we started with, plus the mass of the object that we've thrown in. Okay? And the problem is that when we look at the black hole, the only thing about it that we can see is the mass. So what that means is if I throw this perfect, very little information object in, I'm going to see a new black hole with this mass. Alternatively, if I throw the cow in, I'm going to see the same result. So the external universe is experiencing a loss of information. The information that this was a cow versus just a perfect sphere seems to have disappeared from the observable universe. Now, right now, that's not a problem, because what you could say is, well, this interior of the black hole is still part of space-time, albeit we can't see it. So the information that we threw in is still in the universe. It's just that we can't see it. Okay? And maybe quantum mechanics and unitarity really cares about everything. Okay? So that's a perfectly adequate explanation until you remember what?
It will evaporate.
That a black hole will evaporate. And more importantly, when it evaporates, the radiation that it gives off is purely thermal. That is, it's only going to be dictated by a temperature T, which is only determined by the mass of the black hole. So if we wait long enough, this black hole into which we've thrown either this or this will be gone, and the only thing left is the radiation that came out. But the only information that radiation carries was the mass of what went in. That is the black hole information paradox, which was discovered shortly after Hawking realized black holes were radiating. Okay? Now, I don't want to come here and tell you about black hole information paradox. I want to come here and tell you about how it was resolved. And it has been resolved. Okay? But once this was observed, there was immediately put forward two camps on how this problem would eventually be addressed. On the one hand, there was Hawking and Kip Thorne, which many of you have probably heard of. And their suggestion was the story is true, and unitarity is violated. Man, Jacob, you picked the wrong time to walk out. That was crux, but anyway, it's fine.
Just watch it later.
So their side of the argument was the story is true, and information is truly lost, and therefore unitary evolution just doesn't happen. Okay. On the other side was Preskill, a quantum computation expert, and a lot of others, but most notably Susskind, Leonard Susskind. And their counter was that unitarity is preserved. The story is wrong. Okay? And there were some other arguments, some other possibilities put forward. People had this idea that maybe once the black hole it's evaporating, it gets small enough, at the very, very last stage of evaporation, it's sort of black hole supernovas the information out. Or once the black hole completely evaporates, maybe there's actually some remnant thing left there, which is encoding the information that you can't get from the temperature. Okay? So those ideas were seriously considered and eventually ruled out. So it really fell to these two sides of the debate. Okay? Either unitarity is preserved or it's not. And Suskind's approach to it was, and Susskind took a cue from string theory, he said, well look, here's what I think is going on. I think when you take this object and throw it into the black hole, yes, the object is eventually going to get squashed in the singularity at the center. But the information about that object is somehow going to be smeared on the horizon of the black hole. Somehow it's going to be, the information itself is going to be preserved at the horizon in a way that eventually it could be re-extricated once the black hole evaporates. But of course that immediately creates an interesting scenario because these are three-dimensional objects. Okay, three spatial dimensional objects. Of course, everything lives in four-dimensional space-time. So the information in them is three-dimensional information. But the surface area of a black, or the surface of a black hole is how many dimensions? It's two. So Suskind's proposal was that somehow the information in three-dimensional systems can successfully be encoded in two-dimensional systems, and that, of course, is the notion of holography. So Susskind suggested that the resolution would involve some holographic argument. Okay, he wasn't precise in exactly how holography would fix it, but he knew that holography had to play a role. And again, this was inspired by Suskind's familiarity with string theory. Okay, I mean, Susskind was a string theorist, but holography was something that had already been sort of seen in certain aspects of string theory. Okay, so it turns out that the debate was somewhat settled in 1997. Because in 1997, Maldacena put forth the ADS-CFT conjecture. And the ADS-CFT conjecture, in a nutshell, says the following. If I have gravity in an asymptotically ADS space-time, where ADS is a space-time which has negative constant curvature. There's a technical definition, it's not that important. It's asymptotically ADS, so that means if you get far out, it looks like ADS, but of course, somewhere in here, something interesting non-ADS-like could happen. But what Maldacena proposed was that gravity in this scenario is completely encoded by a conformal field theory, which is just a fancy quantum field theory, on the boundary. And the important aspect of that is that it's non-gravitational. Okay? Now, why does that resolve this conflict? Well, here's an asymptotically ADS geometry. What is that?
Black hole.
That's a black hole. So, the geometry of a black hole, what's in here, and everything that happens, its evaporation, its formation, its evaporation, all of that can be completely described by a non-gravitational quantum field theory. Now, what's important about non-gravitational quantum field theories, in fact, what's important about any non-gravitational quantum system, is they're guaranteed to be unitary. So the two sides of the debate were essentially sorted once this duality was proposed, because gravity, no matter what's happening, even if there's something effed up like a black hole, it has to be unitary, because it can be described by something which is definitely unitary. Okay? Now, the problem with this is that this correspondence is extremely difficult to work with. It's very hard to figure out what exactly on the boundary corresponds to what in this thing we call the bulk. So the details of exactly how this resolved the problem were still to be borne out. But the ADS-CFT conjecture itself, which everybody pretty much very quickly accepted, said that these guys were the winners. Okay? And there was something wrong here. All right? Now the actual details of how this actually worked took another 7 years, which eventually ended this 30-year debate, starting roughly in 1975. And so, in 2004, Hawking came forward and said, I figured it out. I know what the hell's going on. Okay? So this is what Hawking proposed. Oh, and by the way, I should say that the ADS-CFT conjecture obviously supports Suskind's suspicion that holography would play a role, because the ADS-CFT conjecture itself is holographic. This is a volume, it's a bulk, and everything in here is completely captured by what's going on the surface. That's holography. Okay.
Who made the ADS-CFT?
Maldacena. Juan Maldacena. Okay. Maldacena, it's funny, Maldacena wrote a paper, and it wasn't entirely clear that he knew what he did. And then Witten came along and wrote a paper right afterwards saying, holy shit, this guy just did something important. And then it's like, I think this paper might be one of the most cited papers in the Annals of Physics. It's ridiculous. But anyway, okay. All right, So what did Hawking propose? Well, this is where it gets interesting. So what Hawking proposed was, we're interested in the dropping something into a black hole, and then eventually what the story of like that black hole radiating away and how that finally ends up. So what Hawking said was, you know what we should do? We should think of this like a scattering event. So what he proposed was, let's take stuff to form a black hole and a spherical cow, which we know is a spherical cow because it's got 4 legs, a head, a tail, and spots. Okay? And the stuff to form the black hole is going to come in, and the cow is going to come in. And then there's going to be stuff eventually that comes out. And what we have to do now is fill in the details. Now the key is you have to fill in the details in all possible ways of filling in the details. So that means that there is one story where this thing never forms a black hole. Maybe some other interesting stuff happens. Okay, the cow gets blown to bits by a howitzer in World War II or something, I don't know. So maybe the stuff that comes out is not exactly these two things, but the important thing is there's no black hole. Okay? But of course, you also have to include the possibility that this does form a black hole. And then the black hole radiates and you get stuff out. And then there's a lot of other possibilities, okay? Hawking mainly focused on these two. The process where this does collapse to form a black hole, and then you throw the cow into it, the black hole evaporates, and then you ask what's left over, versus this thing and the cow this never forms a black hole, something happens, and the same stuff ends up coming out. Okay? And we're not worried about the mechanism. But the point is, both of these possibilities and others must be included in the calculation. Now what's interesting, and what Hawking pointed out, is that if you start with this part of the calculation, this part of the calculation obviously conserves information. So information is preserved. Or I should say unitarity is preserved, but I'll just say information. Okay, because there's no black hole. Outside of black holes, we know everything works out fine. Okay? And then the interesting part is that for this part of the calculation, it turns out that the contribution from the black hole to any quantity that you might ask about at infinity. So these things are at infinity in the past, and the stuff you're observing is at infinity in the future. This is called an S matrix or a scattering matrix. And you kind of have to go to infinity to make sure you don't allow yourself to tap into what's going on here. Any of the questions you ask about at infinity get a contribution from this geometry, which is 0. So the problem is resolved by realizing that if the only thing you're asked to think about is, how do I explain the stuff here based on the stuff here? And remember, you're never allowed to ask which of these happened. In the same way that you're never allowed to ask which of these things happened. You're only allowed to observe what goes in and what comes out. Then, with those being the only observed quantities, the information is preserved. Unitarity is preserved. Okay? So this was Hawking's proposal in 2004. It ends the debate, but what's interesting about it is that this solution had already been proposed 3 years earlier, in 2001. And that was a paper called Eternal Black Holes in Anti-de Sitter Space by Maldacena. And what's hilarious about this is that you guys have been reading that paper extensively and perhaps never realized that it was written to address this problem. But that's what Maldacena was originally trying to do. Maldacena's paper was working in the context of 2 plus 1 dimensional, so a lower dimensional case with a very special black hole called a BTZ, or a topological black hole, which makes the calculations very, very simple. Hawking did something very non-trivial in 2004 because he generalized the argument to higher dimensions, in fact 4 dimensions, the space-time we live in, okay? But the seed of the idea had already been presented 3 years earlier in Maldacena's paper, although, you know, still not completely accepted and confirmed. Okay, so that's it for today. Okay.
We got it all.